This is a video on comparative volcanism. So comparing volcanism on Earth, Mars, and Venus, and it's specifically aimed at my planetary geology students at Mississippi State University. All right, just a quick reminder, while you're doing this, you should have out your volcanism notes sheet that was in your packet. If you didn't get this, you can print it from our Google Drive. So a reminder about magma composition and gas content. We're reminding you that the more silica-rich your eruption, the more viscous your eruption is going to be. So what I mean by that is that silica tends to form chains, and those chains are interlocking. So if you think about the proteins in a scrambled egg, how when you cook those proteins, they intertangle with each other, and that's how you get a fluffy scrambled egg. For silica, silica also forms chains, and so the more silica you have, the more chains you get. Think of it like a big bundle of Christmas lights, and so that bundling and thickening is going to make your magma or your lava more viscous. So it's going to have more resistance to flow. And we see this in volcanic chains, especially that are, near subduction zones where you have rhyolites and those types of andesites that are developing, those types of lavas. Those are really silica-rich lavas, and they tend to have really thick flows. Also, with a really silica-rich lava, you tend to build more gas. And I'm sorry if you hear a kid crying in the background. My son is really upset that I'm filming this video instead of playing with him. So the more gas you have, the more explosive your eruption is going to be. And that's because that gas is building, and almost like shaking a bottle of Coke and then opening it up, it's going to be explosive. So silica and gas work hand in hand. The more we have of both, the more viscous, the more eruption we're going to have, the more explosive it's going to be. So today we're going to look at changes in eruption and volcanic edifice, so fill in eruption and edifice here, that are caused by gravity, atmospheric pressure, and surface temperature. And what I'd like for you to do is you can pause the video here and fill in these values for gravity, temperature, and pressure for these three planets. Notice that gravity on Earth and Venus is about the same, but about a third of that on Mars. And that surface temperature changes across each planet. So if Earth, our average surface temperature is 58 Fahrenheit, Mars is much colder than that. Venus is much, much warmer than that. And then pressure, this is the pressure that we feel at the surface, so that you and I feel when we're walking around in our everyday lives. If we think about that as being 1 bar on Earth, Mars is about 1/200th of that, and Venus is about 92 times of that. So let's talk about the way that gravity affects eruption and edifice first. So the first way is through buoyancy of the magma. Buoyancy of magma. All right, so let's think about it like this. Buoyancy force is the upward force of a fluid. It's how bad that fluid wants to make it to the surface. So let's just think about one of these magma chambers. It doesn't matter which one, but we can think about these magma chambers and how bad they want to make it to the surface. How bad they want to make it to the surface is caused by the difference between their buoyancy force and the force of the rock going down around them. So if I am a liquid down here at depth, this rock around me is not a liquid. It feels really different than I do. So I'm going to want to make it to the surface. I'm going to want to kind of be in a more equilibrium type environment. So if I have a bunch of gravity, if I'm pushing down on this rock around this volcanic unit, then that volcanic material is going to propel to the surface. It's going to move through any possible crack in the rock that it can and make it to the surface. So the more I press down, the more buoyant force, the more that magma is going to want to make it to the surface. But if I don't push down very much, then that magma kind of has no motivation to make it up to the surface. So the more gravity you have, or increase G, you increase, or let's say decrease, you decrease the chamber depth. If we decrease gravity, then we increase the chamber depth. So this is going to be deeper, and these chambers are going to be shallower. They're going to propel toward the surface. It also affects the way that gas behaves. So in a magma chamber, gases emerge toward the surface, and more gases emerge the closer you get to the surface. So this is just like opening up a bottle of Coke. When you first get a bottle of Coke out of a vending machine, you may not see very many bubbles because inside that bottle, it's pressurized. But when you take the top off and you hear it fizz, what you've done is you have decreased the pressure. And so bubbles and volatiles can leave that solution when that pressure drops. So what that means is if we decrease gravity, then gases are going to be able to emerge at greater depths, and you're going to end up with a more explosive eruption. So if we decrease gravity, we increase our gas and we increase our explosiveness. It also affects the flow thickness. Gravity is going to push down on the lava as it flows out of the volcano. It kind of pulls it downhill. So the more gravity we have, the longer our flow. And the less gravity we have, the shorter the flow. Finally, it also affects the plume. The less gravity we have, the more the particles can be lofted into the atmosphere, so the greater the plume. The more gravity we have, the lesser the plume. So let's do some sketching. Earth and Venus have really similar gravities. So in terms of how gravity is going to affect the volcano, we don't really have to think of these as being separate. So let's go ahead and sketch this. On Earth and Venus, let's see, our magma chamber can be pretty shallow. And we have greater gravity, so we're going to have a less explosive eruption. Our length of flow is going to be longer. And let's see, our plume should be shorter. So this is Earth and Venus from a gravity perspective. On Mars, we are going to have a deeper magma chamber. We're going to have a more explosive eruption because there's more gas. We're going to have less gravity, so a shorter length, which creates kind of a taller, piled up volcano. And less gravity, so our plume should be bigger. So we drew that. So in terms of gravity, this is what we would expect differences to look like. Let's move on to atmospheric density. So atmospheric density is going to affect the emergence of gases from a magma. So again, we're going to see an effect on gas. Volatiles will tend to come out of solution when there's more of a contrast between their concentration in the magma and their concentration in the atmosphere. So if you've taken intro chemistry, you've probably seen something like this, where if you have a high concentration of water molecules and a low concentration on this side, things will move from high concentration to low concentration, or the water will flow from over here to kind of lower the concentration on this side. So water flow will go this way. If the particles were going to flow, the particles would go from side 2 to side 1. The idea is that the concentration kind of wants to equal out. So when there's a really large contrast between the volatiles in the magma and the volatiles in the atmosphere, meaning that there's a lot of volatiles, a lot of gases in the magma and not very much in the atmosphere. Let's say here's magma and here's the atmosphere. If there are a bunch of volatiles in the magma, but not very much in the atmosphere, those volatiles will want to move into the atmosphere. And so that means that the thinner the atmosphere, the more the gases want to come out of solution and the more explosive your eruption. So the less atmospheric pressure, the more gas comes out of solution and the more explosive your eruption. It also affects the plume, kind of like we had talked about with gravity. So when a volcano produces that plume has to push through the atmosphere to go up. So the thicker the atmosphere, the harder that's going to be, and the less that plume is going to be able to develop. So the less atmospheric pressure you have, the larger your plume is going to be. All right, so let's think about the difference between Earth, Mars, and Venus, just in terms of atmospheric density. On Earth, we said it was 1 bar, Mars was 1/200th of that, and Venus was 92 times that. So let's just draw a basic plume, medium-sized plume for Earth. Okay. On Mars, where the atmospheric pressure is much less than that, we're going to have a much larger plume. It's going to be more explosive, a greater plume. On Venus, where the atmosphere is 92 times that, we're going to end up suppressing that plume. So that's a bit of drawing. All right, last thing to affect the edifice and the volcanic style of eruption is the surface temperature. So the first thing that it's going to affect, once again, is the plume. Magma in colder air is going to have a higher temperature contrast with the temperature between the magma and the atmosphere. So magma is obviously really, really hot. And so as that magma comes out, if it's really hot and the atmosphere is really cold, we're going to get a big plume and a big ash cloud as heat rises. So if we decrease the surface temperature of a planet, we are going to increase plume height. And if we increase the surface temperature of a planet, we are going to decrease the plume height. The other thing it's going to affect is that flow length. You might be able to kind of predict this, that if the surface is really warm, that lava is going to stay runny longer and it's going to run out and have a really nice long flow. Whereas if the planet is really cold, that lava is going to freeze up pretty quick and it's going to have a shorter length. So let's draw some predictions based on temperature for what the surface should look like. So Earth is kind of like the middle ground because Mars is going to be colder and Venus is going to be warmer. So let's give ourselves a medium length of both of these. Medium length flow and medium length plume. None of this is to scale, by the way. Okay, so for Mars, we have less temperature, less heat on Mars. So here we're seeing a decrease in temperature, and here we're going to see an increase in temperature. By decreasing temperature, we're going to increase the size of the plume. And by increasing the temperature, we're going to increase the length of the flow. By decreasing the temperature, we'll decrease the length of the flow. Venus, we increase temperature, so we have a smaller plume. And we increase temperature, so we have longer flows. All right, so make sure you've drawn that. Okay, so overall, we can start to see a pattern arise about how gravity, atmospheric density, and temperature work together to create themes on volcanism. So Mars, for example, looks like it tends to have shorter flows, and they tend to be really explosive, like big clouds. We see big clouds showing up for Mars in each of these categories: short flows, big clouds. And for Venus, the theme seems to be really small plumes and really long flows, especially compared to Earth and Mars. Okay, so on Mars, then we should see really big volcanoes, really explosive eruptions. And on Venus, we should see really flat volcanoes with really long lava channels and things like that. So if that's the case, where are the super volcanoes on Mars? I mean, we have Olympus Mons, we have Tharsis Mons, but where are our really, really big ones? Those super explosive, high plume, short flow volcanoes, where are they? And I think the answer that the planetary community has come to is that some of these things that we thought were impact craters are not impact craters. That this, for example, may not be an impact crater, but that it's a caldera that was characterized by a really high plume and a really short flow. So, for example, this was once thought to be an impact crater, but now we think that it's a caldera. And if you have taken my class and you've worked through impact crater morphology, you can kind of see how this doesn't look like a regular impact crater. And I know that there's a scale here that this is 20 kilometers, but we don't see any little bit of a central peak. Everything looks kind of broken and collapsed in. And that's a feature of a caldera, not really of an impact crater, where you would expect things to be blown out by a point source explosion. And this is also why we observe Olympus Mons. So Olympus Mons, with its massive caldera, this thing can build and build and build from flows over time. And volcanoes on Venus tend to be these kind of pancake dome shapes, and that's because those flows can be really long. We can even form these long lava channels on Venus, and we don't have huge ash clouds. We just have these little pancake type volcanic features. All right, thanks. Bye.